molality is important in determining the change in colligative properties of solutions. Colligative properties. What are colligative properties? Oh, boiling point and freezing point. Okay? Sharon, you did not answer again, Sharon. Okay, molality is the moles of solute per kilogram of solvent. That is important in determining the boiling point and freezing point of the solution. Now, I encountered an incident wherein there was brine solution in the ammonia refrigeration facility, and, oh, actually it's an ice plant, I'm sorry, it's an ice plant. Why do they use brine solution? And they use that to freeze the water in the boxes. Why? Because it has a lower, way lower freezing point than actual water. So the water itself will freeze first, the brine will not. Okay? That's because of molality. Moles of solute per kilogram of solvent. Oh, the dreaded parts per million. Woo. You encounter parts per million all the time, but do you know how to use it? That's another story. Okay, parts per million is the weight of the contaminant per million weight parts of the mixture. Keep that in mind, the weight of the contaminant per million weight parts of the mixture. There's no getting around it. You have to be familiar, when you want to do calculations in hazmat chemistry, you have to be familiar with these prefixes. And remember the ppm, it's the weight of the contaminant per million weight parts of the solution, right? Or the environment. There's no going around it. You have to be familiar with these prefixes. Tera is 10 to the 12th, giga is 10 to the 9th, mega is 10 to the 6th, kilo, and so on and so forth. You see, centi is 10 to the minus 2, deci is 10 to the minus 1. 1 cubic centimeter is equal to 1 ml. Don't confuse that with milliliter. I'm sorry, milliliter, because it's got a milli, but milli is 10 to the minus 3 of the liter, okay? Not of the centimeter, because it's a linear unit of measurement, whereas liter is a volume unit of measurement. But there's no going around it. You have to be familiar with these, at least up to giga and up to nano. Because tera and pico, I don't know, with the nano industry right now, the nano materials and everything, maybe they can come up with pico in 5 years. So you need to know these prefixes. You need to, and again, my 4th grade daughter is already understanding this, and I said, there's no getting around it. You have to memorize this, okay? There's no, and it's the same thing. In CUPA Inspectors, you need to know this. For ppm, look, any combination that will lead to a difference of 6 powers of 10 is the ppm, okay? Keep that in mind. We have an example later. Again, any combination that will lead to a difference of 6 powers of 10 is already the ppm. Example, 3 grams of arsenic in 1 megagram of solution is 3 ppm. Why? Because 1 megagram of solution, there you go, is 10 to the 6th power already, right? Mega, 1 megagram is 10 to the 6th, and gram is the unit of measure. So 3 grams per 1 megagram, 3 grams per 1 megagram, already 3 ppm. You just remove gram per megagram, and it's already ppm. Next, 5 milliliter of hydrochloric acid in 1 kiloliter of solution is 5 ppm. Because milliliter in 1 kiloliter, milli is 10 to the minus 3, kilo is 10 to the 3rd. The difference is 6 powers of 10. Therefore, you remove it, it's just 5 ppm. 7, oh, this one is very, this example is for the meth heads. It's very familiar. And some people laugh right away when I say meth heads. I wonder why. But anyway, 7 micrograms of meth in 1 gram of mixture is 7 ppm. Because microgram in 1 gram, 6 powers of 10, remove that unit, it's already ppm. Okay? No, because for meth, I don't know if you attended, or maybe it's together with this session, for methamphetamine. They do wipe samples, and the wipe samples are supposed to give you in units of microgram per 100 centimeters square of wipe sample. Okay? So micrograms. So that's why I said there's no getting around it. You just have to be familiar. That's why I prefaced this one. It says be familiar. As CUPA inspectors, you just have to be familiar. You know, when you're dealing with RPs and you project an image that, hey, I know PPM or this and that, it kind of looks good, especially to San Bernardino County, right? Thank you. I just pick people. I was trying to get the face of somebody I met yesterday at lunch, but they're not here. Too bad. They're from Lake County, and I thought that Lake County, Lake County is like way north of San Francisco. And I told them, is there somewhere north of San Francisco? I mean, and they laughed at me because, you know, yes, there is. It's a town of 12,000 people. All right. Well, we have 10 million, so. Question. An aqueous solution of 100 milliliters contains 0.02 gram of sulfuric acid. What is the parts per million? Aha. You see, I said there's no getting around chemistry. You will always come up with, you know, applications of chemistry as a CUPA inspector. I know that this is like, I won't use this question or things like that, but when you go to an RP and they explain to you, okay, this is what I do in the plating solution, this is what I do, this is what I add, this is what this and that, I add those components together, then you have an idea, okay, what is the concentration of that material in that solution, okay? An aqueous solution of 100 ml contains 0.02 gram of sulfuric acid. What is the ppm? Answer. Listen, assuming a density, it's very small quantity of sulfuric acid, so we can assume the density of 1 gram per milliliter, 1 gram per cc. 100 milliliter is equivalent to 100 grams. You see this? 100 ml, right? That is of solution. Assuming the density is 1 gram per ml of the solution, that means for 100 ml, there will be 100 grams. So that's equivalent to 100 grams of solution, right? But then this one is 0.02 gram. Is 20 milligrams. You know, you just convert gram into milligram, 10 to the minus 3. Or 20,000 microgram. Divide 20,000 microgram by 100 grams, and you get 200 microgram per gram. Now, microgram per gram, is that a difference of 6 powers of 10? Yes, it is. Yes, it is, Sharon. Yes, it is. I'm sorry. Am I picking on you? But please, if I'm offending anybody, please tell Karen. Karen is from LA County. She will shut me up. The answer is therefore, what? 200 ppm. Because it's already 200 microgram per gram is a difference in 6 powers of 10. So the answer is therefore 200 ppm. Great. The LEL of benzene, to fire inspectors, the LEL of benzene is 1.1%. Should you enter a room with a known benzene atmosphere when your 4-gas meter reads 2200 ppm? See, listen. There are direct reading instruments out there, right? But sometimes, oh no, not sometimes. All the time, it is calibrated to a certain calibration gas. When I taught hazmat chemistry in UCLA, they always tell me, we're not going to use that and this and that, the benzene atmosphere. So, because, but then I said, I'm sorry, they said that I should discuss more about the direct reading instruments and then how to convert from one calibration gas to another. I mean, it's just simple multiplication. So, I mean, there's just conversion factor. So you just got to be in 3rd grade and you know it already. But then here, when your 4-gas meter reads 2200 ppm, let's just assume that this was calibrated on benzene, okay, in benzene. And we know for a fact that there was a spill of benzene from the responsible party. There's a spill of benzene in the room and so on and so forth. So, and then your direct reading instrument reads 2200 ppm. So what do? 1.1%, 1.1% is 11,000 ppm, right? 1.1%, again, 1.1% is 11,000 ppm. That means the LEL of benzene is 11,000 ppm. Follow me so far? Yes. Thank you. The safety factor for entry, correct me if I'm wrong, I think it's 10% of LEL, right? 10% of LEL. So, you need to get 10% of 11,000, which is 1,100. Since the room is 2,200, then the answer is no. You should not enter the room. Practical application of what you know as CUPA inspector for chemistry, your chemistry knowledge. You know, I've been with LA County Fire, with Hazmat, like for 17 years. Don't calculate, okay? I'm old. But anyway, really, my knowledge of chemistry really helps me a lot. When I go to a responsible party and they explain to me stuff, and I am familiar with the words that they are using, it makes you feel good in doing your job because you're familiar, okay? So when you know how to convert, you know, 11,000 ppm, and then you know that 10% is the safety factor, then there's the answer. Another need to be familiar with, conversion factors. There's no getting around it. You have to be familiar with this. English to metric and vice versa. But as a CUPA inspector, I found out in my 17 years that all I need to know, as long as I know the next slide, are these three things. 1 inch, you're supposed to know, is 2.54 centimeters. My 4th grade daughter knows that, okay? 1 gallon is 3.785 liters. 1 cubic foot is 7.481 gallons. 1 pound is 454 grams. This is linear, volume, and weight. If you know all these numbers, you'll get by in Hazmat calculations. Okay? All you need to do is just memorize all these numbers, and you'll get by. Be aware that you multiply and divide so you can cancel units as numerator and denominator. For example, see, look, 1 gram per ml, you multiply and divide using any of these conversion factors to come up with pounds per gallon. 1 gram per ml, you multiply it by 1,000 ml is equal to 1 liter. You see, so the ml will cancel out the ml in the numerator, cancel out the ml in the denominator. Liter, there's 3.785 liters per gallon. So liter will cancel. And then 1 pound, there's 454 grams in 1 pound. So the gram here will cancel out the gram there, and what will be left is pounds per gallon. And you see, 1 gram per cc is 8.34 pounds per gallon. And this is exactly what you do in any of your Hazmat calculations, dimensional analysis. Even if you go to like engineering calculations like heat transfer here and there, convection, conduction, specific heats and things like that, you always use dimensional analysis to cancel out numerators and denominators. That's very important. Estimation of vapor density based on ideal gas law. We're getting into physical chemistry. Oh, wait. I think I'm getting slow. I have to speed it up because the more exciting portion is lunch, right? So, and I don't want to keep you up. And the more exciting portion of the presentation is the case studies. Welcome, ma'am. Thank you very much for coming. Estimation of vapor density based on ideal gas law. Ideal gas law is PV equals nRT. Everybody knows that. N is the weight over molecular weight. So it can also be converted to P times molecular weight is equal to raw RT, where raw is density and MW is molecular weight. Average molecular weight of air is 29. What is it based on? Based on 21% oxygen and 79% nitrogen. And then there are some few here and there, carbon dioxide stuff. So the average molecular weight of air is 29. Now, if the molecular weight of contaminant is greater than 29, will most likely behave as a heavy gas. Again, if the molecular weight of a contaminant is greater than 29, it will most likely behave as a heavy gas. It will settle down. It will not float in the air, okay? That is, of course, assuming ideal gas behavior. Now, again, another one. Assuming ideal gas behavior, conversion of gram per cubic meter into ppm is this formula. Now, this formula, keep in mind, is only useful for gases or vapors. Chlorine gas, ammonia gas. Do not use it for sulfuric acid. Okay, I did not teach you to use this for liquids, okay? Use this only for vapors or gases. So, if you have the IDLH given to you in gram per cubic meter, then, and you want the ppm, why? Because your direct reading instrument is in ppm. Then, you just have to convert using this formula. How do you use that? Question. Half a pound of chlorine was released inside a 10,000 square foot warehouse with a 12-foot ceiling. Higher than this, I think. Higher. Assuming chlorine behaves as an ideal gas and it mixes homogeneously with air in the room, what is the ppm concentration? How do we do that? Convert 0.5 pounds. You multiply it by 454, you get 227 grams. Convert 120,000 cubic feet. Where did I get 120,000 cubic feet? Anybody? Anybody? Square feet and height of the building, correct. So 12. And your name, sir, is? Gary from PG&E. Oh, okay. So I will not mention Sharon's name anymore. It's going to be Gary from this on. So you convert 120,000 cubic feet. How do you convert? Remember those numbers that I just told you? Those you can get by with those numbers. 12 inches per foot and 0.0254 meter per inch. And then you raise it to the third power so that it becomes cubic inches and it becomes cubic foot and cubic meter. Follow so far? I hope so. So therefore, what is the gram per cubic meter? When you convert this to cubic meter, it's 3398, and you already have the grams. Therefore, gram per cubic meter is 0.0668. Believe me, I use a calculator, so that is it, okay? Now, what is the ppm? Using the formula that we have over from the previous slide, you just multiply 0.0668 by 24,500, then you divide by the molecular weight of chlorine, and you get 23 ppm. What's the IDLH of chlorine? Yay, 10. So we just have to run. Make sure that we don't enter into 23 ppm, okay? Buffer solutions. It's just to give you an idea of what a buffer solution is. It's actually a solution just such that the pH remains constant, a short range. Now we go to the reaction chemistry. Reaction chemistry. As CUPA inspectors, if you're just inspecting a facility and then you come across something steaming, then there must be some reaction going on. It's better to know types of chemical reactions. Now, listen. There's a large diversity of chemical reactions. So that's why there's like overlapping ways of classifying them, okay? So this is just one of them, one of the ways of classifying them. Synthesis or direct combination. A plus B equals AB. Hydrogen plus oxygen becomes water, but with tremendous amount of energy, okay? So it's actually an endothermic reaction. Endothermic reaction, you need energy. That's a synthesis. Decomposition is AB. Becomes A plus B. Listen, now there are again several subcategories of synthesis and decomposition. Like hydrogen peroxide can decompose into not hydrogen and oxygen, but water and oxygen. Okay, but there will be a slide for an incident that I went to hydrogen peroxide, which we will discuss later. So that's why. Okay, let's finish off. Single displacement is A plus BC equals AC plus B. That's ordinary. Double displacement is AB plus CD equals AD plus BC. Acid-base reaction, it is acid-base reaction is a form of double displacement. For example, hydrochloric acid plus sodium hydroxide becomes sodium chloride plus water. This is just a, you see, I put HOH there because OH stands for AB plus CD. So it's a form of double displacement reaction. And most, if not all, acid-base reactions are exothermic. And CUPA inspectors should know that. That's why you cannot combine acid and base in the same storage area, because when they combine, heat. And then if there's anything combustible, fire. Okay? Oxidation reduction or redox. For example, this is where the oxidation states that I was talking to you about. Remember, the oxidation states that the charges of the chemicals will come in. Thiosulfate plus iodine becomes tetrathionate and some iodide. You see, iodine is the oxidizing agent. Why? I'll explain to you later. Combustion. Combustion is a special redox reaction, okay? Organic reactions, way too many to mention. There's too many. There's electrophilic substitution, electrophilic addition, nucleophilic addition, and so on. And then it depends on who discovered the reaction. And then oxidation reduction